So you can plug all these in, you get these, and now the new input variable is omega 2 at that position, and what you're interested in is omega 3 and V4. Okay? Now you might think, well, wait a minute, the units on this were different. How in the world can I just still multiply it by omega 2? Well, if you think of it, R4 prime is dr4 divided by d theta. So if you times by omega 2, it's d theta 2 divided by dt. Those cancel, and you still get the derivative of the displacement with respect to time, which is v4. So it'll always work. You don't even need to worry about the units. If you just find the first order kinematic coefficients, multiply by the input variable, you've got what you need. Okay, so here is another example. If you recall, we did the position analysis in a previous topic, in topic 2. And you got these, you solve the vector loop, you got the two component form, and we're just going to assume, you did position analysis and you know everything. So I give you a theta 2, you know theta 3, and you know R3 now, okay, from position analysis. Those were the two question marks. Two things you didn't know is theta 3 and R3, but now you know it, okay? So now you're ready for velocity analysis. So take the derivative of these with respect to the input variable theta 2. So put me on pause and take the derivative of that. Okay, now, but you might, just a quick hint, if you haven't put me on pause just yet, don't forget to use the product rule, because remember, this one and this one are two functions that change. The R3 changes with respect to theta 2, and theta 3 also changes with respect to theta 2, as well as with respect to time and everything. So you've got to use the product rule here as a hint. Okay? Okay, so if you haven't done it by now, and you don't want to put me on pause, I'm just going to give you the answer. If you take the derivative of this with respect to theta 2, you get this. And here's that product rule I was telling you about. R1, when you take the derivative, goes to 0. Because it's a constant. Okay, so do the same thing with this one. And beware of that product rule. Okay, put me on pause. Okay, the answer is this. So confirm that you got that right. Now that you've done that, the next thing to do is to put these into a matrix form. Okay, so feel free to put those in matrix form and put me on pause if you've already done that. Here is the solution. Remember, the key is everything that doesn't have a first order kinematic coefficient in it, subtract it over to the other side, and then pull out the things with first order kinematic coefficients, and you will get the Jacobian matrix. This big complicated matrix is the Jacobian of that particular one. It'll show up, like I said, in position, velocity, and acceleration analysis. Take the and notice we have all the variables you need. We have theta 3, we have R3, we have everything in there. We have R, everything's already, we have it from position analysis. We obviously have theta 2 as well, okay? So you invert it, we have everything you need in there. So you can solve this because you've already done position analysis. And now guess what? You just multiply these by omega 2 and you've got it, okay? Okay, so this is just a summary slide of what I just taught you, right? And so you can read that in your own time, but I'm not going to spend the video time reteaching what I did. But this is basically a summary of the first order kinematic coefficient approach. Super useful. Definitely will be on exam. Is very important for this class, and is much better idea than solving things by hand and then taking the derivative of them with respect to time. Okay. All right. Okay, so this is also a chart that's useful. It tells you all the different kinds of first order kinematic coefficients you can get, because sometimes your input variable, like theta 2, is an angle. That's very common. But sometimes your input variable is a displacement, r. So for instance, like a slider crank, maybe the input, maybe they label 2 as the slider, the box, and that's the input. It's a linear motor. The input's not always theta, sometimes it's displacement. And then the output can either be a theta or it can be a displacement, right? So if the input and output are thetas, then this is a d theta with respect to d phi, which is an angle, right? And so that's radians divided by radians, which cancels and it's unitless, okay? So there's no dimensions to those. and you still multiply by the input variable, whatever that input variable is, whether it's a displacement or a rotation, and you'll get the right answer. So you don't really need to worry about dimensions and units and stuff, but it is good to know and to kind of be aware of, okay? But if you just follow the approach blindly, it'll always work, okay? But now, in the case, say you had an input displacement and an output theta, which is if you drive the slider and the slider crank, then you get, then you get a d theta with respect to dr is what it would be, right? Because here phi is an r. And so that would be radians divided by length. As you know, radians are actually not units, so they're actually unitless inherently. If you don't know that, think of what the definition of radians. It's basically how many. It's like if you take 2 pi, 2r pi. That's the perimeter of a circle. Then you divide that by r to find out how many radiuses fit in that circle. And the answer is, of course, 2 pi. That sets up how many radiuses there are in a circle and how many radians. Okay, so you're basically thinking it's perimeter, which is in meters, divided by radius, which is in meters, so it's unitless. But we just call it radians, to give it a name. Okay, so but radians has no unit. Okay, so it's unitless divided by length. So it's 1 divided by length. Okay, now if the output is a displacement, but the input is a theta, then it's going to be the slider crank doing the normal way, where you're driving, link 2. And the output is the slider, like we just did. So it's actually dr divided by d theta, which is a length divided by an angle, which means it's in meters with divided by radians, which is just meters, right? So it's just length. Okay, and then there are instances, like if you remember the 2 sliders we did with the link connecting them, or one sliding on a vertical wall, one sliding on a horizontal wall, or floor, I mean. That the input and the output were both displacements. So you got dr divided by dr, which is meters over meters, which is unitless. So it's dimensionless. The displacements actually cancel. Okay, so so there's only 4 units that kinematic coefficients can have. They're either, 3. They're either dimensionless, or in meters, or 1 over meters, inverse of meters. Okay, but regardless of what their dimensions are, you can always multiply it by whatever the input variable is, be it an r or a theta, and it will give you the answers you want. Okay, so this next topic is about instant centers. Okay, so this is also very important to velocity analysis. It's kind of first of all, you need to know how to find instant centers for many reasons, but the main reason we're pursuing this is so you can do another approach to velocity analysis that's kind of a graphical approach, and you'll need to know how this works. Okay, so first of all, let's teach what is an instant center. Well, first of all, an instant center is say you have 2. So it's any 2 bodies always have an instant center. So it's like you think of a pair of bodies and where's their instant center. Okay, so say one body is I and one body is J. Well, the instant center will be defined as a point P, ij, or pji. The order doesn't matter at all. So if it was body 3 and body 2, their instant center would be P23 or P32. It doesn't matter. But so what is that point? It's a point that we're going to find between any 2 bodies. That's the first thing. But it's the point where if it were on body I, it would have the same velocity as that same point if it were on body J. Okay? So for instance, if I took like 2 links and I threw them up in the air at the same time or something, or even if one of them's not moving, say one's fixed to ground and I throw the other one up in the air, and then I take a picture at some instant in time, when I take that picture, there is some point in space where if I think of that point on either body, they would have the same velocity. That is the instant center. And notice I said velocity, not speed. They have to have the same magnitude of speed, but also the same direction. Okay, so same velocity. Okay, and before I tell you what's significant about this point, I just want to really nail this point and help you find instant centers now that you know the definition of it. Being it's like if it were on if that point were on either two bodies you're looking at, examining, that's the point where they have the same velocity. Okay. By the way, said another way, it's the point where the relative or apparent velocity of one body with respect to the other body is 0. Okay, so if you imagine say I take two bodies, 2 and 3, and I chuck them up in the air. If I'm an ant on one, and like that's my reference frame, and I'm imagining not moving, I won't know I'm moving, then relative with respect to that reference frame, the instant center between those two bodies will be the point on the other moving body where that body has a velocity of 0, right? Because if you're an ant on one body, your velocity everywhere is 0 because nothing's moving in your reference frame. Okay, so it's the point in space where the apparent velocity of one body with respect to the other body is 0. So try and wrap your mind around that. We'll do a bunch of examples here. Okay. Okay, so there are some joints. Well, really, anytime you have a joint that's joining two bodies, it's usually really easy to find their instant center, and you can just memorize them. But I want you to intuit this and think through it for some obvious common joints. Okay, and it'll help fortify the definition of an instant center. Okay, but basically the point is I'm going to show you a bunch of joints that the joints by definition two bodies, and we're going to find the instant center of them. And once you get some experience with this, you'll be really good at finding the instant center for joints. Okay, and that'll be important. Okay, so the simplest joint is just a pin joint. One body or link is the ground, the other link is, say, 2, and they're pinned together, so this can only rotate. Well, if I asked you what point in space, if it were attached to either body, has the same velocity? Well, every point on the ground has a velocity of 0 because it's not moving. And so another way to ask the question is where is body 2 have a velocity of 0? Well, the only place where body 2 has a velocity of 0 is at that point. And by the way, we're not talking about angular velocity. We're talking about linear velocity v, where is v as a vector equals 0. So the linear velocity of that point on this body is 0. And of course, the velocity of that point on this body, ground, is 0 too. And so that is the instant center. VA1 equals VA2. Okay? Okay, so, and by the way, also the apparent velocity is 0, but that's obvious because if you're an ant on this, you're not moving, and you're not moving. So it's still, the apparent velocity is 0. But this is a little more interesting. Say we have two links, and they're pinned together, and I just chuck this link up in the air, and they rotate and move, right? About this point A, right? So they're all moving through space. The question is, where do these two links have the same linear velocity? Well, obviously at the pin. So again, VA3 on 3 equals VA on 2. They're coincident points. Their velocity is the same. Therefore, that's the instant center. Now, this is a little more interesting to think about this apparent velocity thing. If you imagine yourself an ant on 2, so it's as if 2 is ground, it's not moving, then you'd say where's the apparent velocity of 3? P3 or slash 2. What's the apparent velocity of 3 with respect to 2 that equals 0? And it would be A. Okay, that point. Okay, so sometimes if you can't visualize where they'll have the same velocity, it's useful to think of one of them being 0, like a ground, held fixed, and finding where on the other body has a velocity of 0, because you're basically doing the same thing, but it's just easier to think about. Okay, so this one's pretty tricky. Say you've got this link 4, and it's got this slot cut in it. It's obviously a circular slot. And right here, this cross here is the center of a circle. If I ask you, well, what's the circle? Is it this circle or this circle? Hopefully after topic 2, you know that it's actually the center of the circle in between. So there's a circle in here, and it's right in between these two circles, the center of the slot, and that is the center of that circle. And of course, when I throw body 4, that slot moves with it because it's cut out on it, and so obviously the center moves out with it. So that point can move with 4, right? Okay, and then 3 obviously slides in that slot. Okay, so the question is, if you imagine 4 and 3 both moving through space, and they're 3 is moving with respect to 4, but they're flying through space, where do they both have the exact same velocity? linear velocity. And that's the instant center. But where is that? It's very difficult to visualize. So let's use our trick of using apparent velocity and just pretend you're an ant on 4. Pretend 4 isn't moving. So is there a place, is there a point that if you imagine it moving with 3, it will have 0 velocity? So that it has the same velocity as 4, because 4 is not moving. So the apparent velocity of 3 with respect to 4, find it where it's 0. Well, if you like to visualize, these points are obviously points of interest, and you can see here I've labeled it P3, 4. We could also say P4, 3. It doesn't matter. But that's obviously the answer. But imagine if I take 3 and I encompass it about there. So imagine that slot, there's a rectangle, a wedge sticking in here that slides on this slot, but then there's something coming out and going down, so you can envision it as part of 3. If 4 were held fixed and 3 were sliding back and forth, you could imagine kind of a link with kind of a pin joint here that wouldn't be moving. So you could imagine that moving. This point wouldn't move. It would have 0 velocity. So that's the instant center where both 3 and 4 will have the same velocity. And if you have a hard time, just visualize it once to derive it for yourself, but then you can memorize it. Every time you see that, that's the instant center of 3 and 4. Okay, this one is super interesting. Okay, this is, you might think, well, gosh, you said every 2 bodies, they always have an instant center. There's always a point where if you imagine it on either body, their velocity is the same, or the apparent velocity is 0. And that's true. But if I gave you this sliding joint, this prism joint, this box on this ground, and it's moving, you could say, well, wait a minute, there's not a place where they have the same velocity, because every point on this ground has a velocity of 0. And you'd think every point on this guy translating has the velocity of the translation velocity. Every point is moving with the same velocity v, and that's not 0. And so you're like, well, these 2 bodies don't have an instant center. Well, you're wrong. Every 2 bodies has an instant center. And you need to understand a little bit about infinity. So remember, I believe it was, topic 2. Near the end, I think we ended with this. I was talking about the difference between rotations and translations. And if you recall, I showed a box, and I had a red rotation line, and it was saying rotate around that. And as I pulled the rotation line, it was rotating about it in different directions. And pretty soon, when that rotation got to infinity, this box was just purely translating. And I proved that a translation is a rotation infinitely far away. Okay? So here we have a translation in this direction. And that would be the same thing as if I took a rotation. Say here's a rotation, and the axis of rotation is coming out at you. And I move that from the joint perpendicular to that direction infinitely far away. Well, that rotation, if you can imagine rotating this block about that point, if it's infinitely far away, is the translation. Okay? And by the way, it doesn't matter which direction I pull it. I could have drawn this point down below here and push it to infinity down there, because you can actually prove that a point at plus infinity is the same point as a point at negative infinity. If there's books that prove and derive this, and I prove it in in the future. And certainly in my compliant mechanism class, but if you have a point moved infinitely far away in both directions, that's the same point. So whether you think about it going up or down, it's the same point. Okay, and you could convince yourself that if you have an axis of rotation down here, off the page, and you try and rotate this, it's going to be the same translation. Okay, as long as it's infinitely far away. Okay, so if you're convinced that this translation is a rotation infinitely far away, then you could imagine this guy encompassing that point, so this link being infinitely long. Just think of a pin joint rotating up there that's stuck on the ground. You could think of the ground going up there too. And you could see if it's infinitely far away, it's still translating with respect to this guy. But that is indeed a point where they have the same velocity. And in other words, that's the point on this block that has a velocity of 0. But yes, you're right. Everything in finite space has the velocity of v2. Okay, so it's a little confusing, but trust me, if you have a sliding joint and you wrap your mind around these principles, its instant center is a point that is perpendicular to the translation at infinity. And it's the exact same thing with a sliding joint here. This rectangle in a slot, it's translating with respect to the slot, and so the instance center between bodies 2 and 3 is a point infinitely far away, just like this. Okay, so again, it's something good to memorize. Okay, now imagine if you have two, say, gears, and they're just rotating. Okay, say it's rolling contact only, there's no slip, so they're not allowed to slip. And if you recall if you recall, remember if you have two bodies that are only in rolling contact, first of all, if they're in contact, you know they're the same velocity along the common tangent, common normal. Anything that's in contact has the same velocity along the common normal. But if it's in rolling only and it can't slide, that means it also has the same velocity along the common tangent. And so that means it has the same velocity. If the two orthogonal components are the same for both, then it's the same. And so we've already proven that this point on 4 and this point on 3 have the same velocity. So that is the definition of an instant center. Like, that's the instant center. That's the point, P34 or P43, where those bodies will always have the same velocity. Okay? And if you think about it, think of like a wheel rolling on a flat ground, and it's only allowed to roll. Then you think, of course, the ground has a zero velocity everywhere. But what point on that wheel has a zero velocity? It's always, the only point that has a zero velocity is the point that's touching the ground it's rolling on, which is the point where it's in rolling contact. Okay, so there's many ways to think about it. But that you can just memorize if it's in rolling contact only with no slip. This guy is the instant center is where they touch. Okay, but now what if we have a scenario where it's rolling and sliding? Okay, so say we have a ground here, and instead of like the wheel that's only rolling, say we have like a bar that has a nice round curve here or something, or it could be a wheel, whatever. But the point is that now we allow rolling and sliding. So this guy can translate and it can rotate. Okay? Well, now it's like, now try and find the instant center where they both have the same velocity. Well, you don't really know, because if it can slide and roll, that's 2 degrees of freedom. And they can do those independently. So you could, if this could slide and roll, force it to just rotate, and then the instant center would be right there. Okay? Or you could force it to just translate and just slide, in which case the instant center would be at infinity, perpendicular to the direction of the translation. And so, or you could do different combinations. Say you slide and roll at the same time at some special ratio. Well, then that instant center would be somewhere along this dotted line, which is perpendicular to where they touch, the common normal. And that's the whole point. If you have a 2 degree of freedom joint, like sliding and rolling, you can't pinpoint where the instant center is unless I gave you the ratio of the rolling to sliding. If I told you it rolls this much with respect to how much it slides, you could pinpoint it, but you're rarely given that information. You're usually just given information that's 2 degree of freedom joint, it's rolling and sliding. And so what you can know from that is that you don't know exactly where the instant center is, but you know it has to lie somewhere along this line. And if it were pure translation, it would be infinitely up there or infinitely down there. And if it were pure rotation, it would be right there. But if it's some combination, it's somewhere along that line. And same thing with this. This is a pin in a slot, so it can roll and translates 2 degree of freedom. You know that whatever line is perpendicular to the direction of translation, the instant center has to be somewhere along that line, but you can't peg it down. But it's still a very useful insight that we will use. Okay? Okay. So I have now taught you a bunch of different joints, and helped you, from these examples, helped you, one, better understand what instant centers are and how to find the instant center for the joint. And hopefully you were able to derive those, and you can, if I gave you new joints, you'd be able to deduce where the instant center was by using the apparent velocity trick, or just find the point where they have the same velocity. And intuit these things, or hopefully you just memorize them, and you get this big arsenal in your head, and you can memorize where these things are. But there's a trick. What if the two bodies aren't pinned together? How do you find their instant center? What if they're not joined together by a joint? Well, then it becomes a lot harder, okay? And we're going to deal with that later. But first of all, if you need to find all the instant centers, you need to know how many instant centers you have. Okay? So say you have this 5-bar mechanism here, and I said I want you to find all the instant centers of this mechanism. Okay? Well, the first question is, well, how many are there that I need to find? Okay? The second question is, okay, well, let's start finding the ones that at the joints, because those are easy. But then there's other ones that aren't at the joints, and I'm going to teach you how to do that in just a minute. Okay? So for this slide, what we're going to talk about is, like, the first question is, how do you find how many there are to find them? If I say, I'm going to give you some mechanisms and say, find the instant centers. Well, you want to know how many you need to find, so you're not just looking forever. Okay? So let's derive an equation that is a function of how many links you have, how many bodies are in the mechanism, that tells you how many instant centers. Okay? Well, the answer is you have as many instant centers as you have pairs, unique pairs of links. Okay? So for instance, for this 5-bar mechanism, you got 5 links. We're going to call the number of links n, so n is 5 for this. And you could think, look, I have, there's going to be instant center pair between 1 and 2, and I'm just going to draw a red line to, like, as a bookkeeping, accounting thing of, like, okay, we've found the instant center between 1 and 2, okay? Well, there's an instant center between 1 and 3. There's an instant center between 1 and 4. And there's an instant center between 1 and 5, okay? And so those are all the pairs. There's 4 pairs you can generate with respect to 1. Okay, but what about 2 and 3? What about 2 and 4? So it gets a little tricky. Okay, but first, if we just want to count all the pairs with respect to the first one, you can find it's n minus 1. Okay, so and check it. In this case, there's 5 links. 5 minus 1 is 4. And you can see there's 4 red lines accounting for all the pairs with respect to 1. Okay, well, now let's go on to the second one. Okay. The second one, you can do a pair. We've already counted 1 to 2, and 2 to 1 is the same thing. So now we got to do 2 and 3, 2 and 4, and 2 and 5. So because we've already accounted for 1 and 2, that's n minus 2. So the red lines that we just added after accounting for all the combinations with 1 is 1, 2, 3, which is 5 minus 2. So 3. Okay? Now we have to add that onto the pairs that link to 3 that we haven't considered. Okay, we've already considered 3, 1 and 3, 2, but now we have 3, 4 and 3, 5. So that's 5 minus 3. That's 2 of the red lines you showed. And then the final pair is 4 to 5. Okay, so we've already considered 4 to 1, 4 to 2, and 4 to 3. So 4 to 5. So that just ends up being 1. Okay, so if n is 6, you do the exact same thing. N minus 1 plus n minus 2 plus n minus 3. You keep going until you get to 1. Okay, and you see the pattern there. Okay, and the sum of all these is the answer. That's x. That's the number of instant centers. That's how many pairs there are, and therefore of bodies, and therefore how many instant centers. Okay, so but like how do you make this a nice equation? Well, there's a little trick. If you add this equation plus itself, but you write it differently. So instead of putting n1 over here, you put it at the end and you put 1 here. You flip the whole thing. And of course, because the order that you add things doesn't matter. So this altogether equals x, and this altogether equals x, just written in a different order. And so now you add this plus this, and what you get here is, well, first of all, on this side you get 2x. Okay, but on this side, check it out. N minus 1 plus 1 is going to be just n. N minus 2 plus n minus 3 is also going to be just n. Because remember, in this example, it was 5, so 5 minus 2 is 3. 5 minus 3 is 2. Subtract them, or sorry, add them, and it's 5. Okay, and that'll always be the case. So you'll just do n plus n plus n. The question is, how many n's? Well, it's always n minus 1. In this case, there's 4 n's, which is 5 minus 1. Okay, so the way you could write this is n times n minus 1 is this side, then divide it by 2, and you get x, which is what you're interested in. Okay, so this is the equation. If you don't want to derive it for yourself, just memorize it. If I give you any mechanism with n links, you take n, you times it by n minus 1, divide it by 2, and that's how many instant centers you need to find. Okay, so for this example, okay, if I plugged 5 into here, you would calculate that x equals 10. So you'd need to find 10 instant centers. Okay, and so your work would be cut out for you there. You'd have to find 10 of them. Okay, and then finding those 10, some of them are obvious and some are not so obvious. But before I teach you how to find the not so obvious ones, which are the ones not at the joints,